Lithium just ends up by itself. It's just the spectator ion, okay? So I just wanted to point that out before we move on. Okay. This is all information that we just said. So I'm going to skip down here. It says, with organic molecules, the lone pair on a nitrogen often acts as a base. So we see that water can be the base. OH minus is a good strong base. Ammonia, okay, is another very common base. All right, ammonia. And we haven't drawn the Lewis structure, but it's right down here for us. This is the Lewis structure of ammonia. You've probably drawn it 100 times. And yes, nitrogen has a lone pair that acts as a perfect base here. So it is going to take the hydrogen from water. Here, look, water for the first time today is acting as an acid. Okay, ammonia is our base. Water is our acid, so it's the lone pair on the base that is going to bind with the H plus from water. And what do we form? What are our products? Well, we get the ammonium ion, NH4 plus. This is another polyatomic ion you had to memorize. And what is left over from water, the acid, when it donates a hydrogen to something else? All we have left is OH minus, okay? So also just want to make point out the difference between the names. This is ammonia, NH3, and ammonium. Don't confuse those names. Ammonia is the neutral compound, NH3. Ammonium is an ion. It's NH4 plus. Starts off neutral. When you add something with a positive charge to it, now it has a +1 charge, okay? So there's just another example of a common base reacting with an acid here. The acid is water. Here is ammonia. Okay, ammonia. Now our acid is not water, but it is hydrochloric acid. Okay, this is a very strong acid. And what is going to happen? Here is our acidic hydrogen. Why? Because Cl, which has all these lone pairs on it, is very electronegative. So this is going to be our partially polarized hydrogen. And the lone pair on nitrogen is going to grab that hydrogen, form a bond. And now we have, again, ammonium. And what's left over from the acid is just the chloride anion, okay? That's an acid-base reaction, that's it. So earlier I told you, remember from chapter 5, we said an acid-base reaction is anything that forms water. Those are acid-base reactions. I told you we were lying to you earlier. We really weren't lying to you. Anything that forms water, it can be an acid-base reaction, but the most accurate definition we can come up with is right here. It's a reaction in which a proton is transferred. So I kind of want you to toss that other definition out the window and replace it with this new definition. This is a better, more accurate definition. An acid-base reaction is a reaction in which a proton is transferred from the acid to the base. Okay, so I've already started drawing arrows like you see down here in these two reactions. B, the blue B stands for base. Anything that's going to be a base, it has to have a lone pair. Okay, now why is that? Why does it have to have a lone pair? Well, the thing is, H plus, it has no electrons. So it has nothing to donate to a chemical bond. So if it's going to form a bond with another molecule, and every single chemical bond that forms in all of history ever has to involve 2 electrons. It has to have 2 electrons. Well, if H plus has no electrons to donate, those electrons have to come from somewhere, and they don't just come out of thin air, okay? That's why both electrons have to come from the base. So that's why we say a base has to have not just one electron, but a lone pair to form a bond with the acidic hydrogen. Okay. In this top reaction, let me erase this. Bases can look all different ways. This base right here is neutral. This base down here has a negative charge. Okay. They don't have to be one way or the other. Okay. An example of one with a negative charge is the OH minus. A neutral one that we looked at was NH3. But just know if it starts off neutral and then it grabs that acidic hydrogen, you're going to end up with a base, okay, that has a plus charge overall. If you start out with a base that has a negative charge and you add a positively charged hydrogen, it's just going to balance to zero, and you're going to end up with a compound that is neutral. No charge overall. Okay. Lastly, what do we have here? This is kind of just what we were talking about. These two reactions up here, having a neutral base or a negatively charged base. Well, it's showing you those examples with ammonia, which is the example we used, and with a hydroxide ion. So this is the neutral. And it says that actually right here. And this is the one that's negatively charged. And it's just showing you with the Lewis structures all the lone pairs on oxygen in OH minus and the one lone pair on ammonia, grabbing the acidic hydrogen from the acid and the kinds of molecules that they make. Okay, and again, it's pointing out that adding a hydrogen creates a positive charge when your initial substance is neutral. But adding a positively charged hydrogen to something that is initially negatively charged just makes a neutral compound. Okay, so don't get it in your head every time an acid-base reaction happens that you're going to get something with a positive charge. That's not true. Sometimes you can just make things that are neutral. Here we made water.